Okay, good afternoon. Let's start lecture. Alright, so we're going to finish the example from previous lecture, okay? And then we'll continue from there. Okay, so here an example from previous lecture. Okay, it's a shaft design type of question. It's actually an analysis type of question. So given the loading condition, given the structure of the shaft, and also some of the working conditions for the shaft. Okay, and we're trying to find a critical location and also trying to estimate basically the life of the part. So that's the question here. Okay, so this question basically will cover all of the topics that we have learned so far. Okay, in terms of finding all the marine factors, in terms of how to find the estimated life of the shaft. Okay. As in the previous lecture we mentioned, there are different locations on the shaft. So which one will be the critical location as the first step that you had to decide on. To find a critical location, then the first step is to draw the moment diagram. Okay. Yeah. We mentioned in the previous lecture that the bending normal stress caused by the bending moment will be more critical than the shear stress caused by the shear force. So, which is why we in most of the shaft design type of question, we will only look at, if you cut a cross section, you will only look at the top and the bottom location as a critical location. Even though the maximum bending moment happens in the middle at here, but because at the B and the C location you have a fillet and you have the presence of this stress concentration factor, so the B and the C will typically be more critical than the center location. And B location has higher bending moment than the C location. So in this question, that's why we only look at the B location to analyze this shaft here, right? So to find the B location, then the question here is, what is the bending normal stress at the B location? Now remember, the working condition is you have a constant force applied here, and the shaft is rotating, right? So you have a rotating shaft. And if you relate this one to the R Moore rotating machine, so that's exactly the situation that you will have this so-called completely reversed loading at each location, actually, not just the B location. Okay, so the complete reversed loading will have this amplitude sigma A, and that sigma A is the normal stress is caused by the bending moment MB at here. Okay, yeah. So the question, let's say we need to find what the MB value is. Okay. In the tutorial and in your assignments, and you probably have practiced quite a bit now, to find this B location, the bending moment, it's actually quite easy. You can just use R1 value times the distance from here to B, which is 250. Okay, yeah. So use R1 value to find this bending moment. But then what is R1 then, right? So R1 is a supporting force, and then this is basically where you use the equilibrium equation to find this R1 here. Now equilibrium basically means, let's say if I'm going to calculate bending moment, if I'm going to calculate the moment about this location at R2, then things has to be in equilibrium, right? So the moment generated by the 6.8 kilonewton from here to here should be the same as the moment generated by the R1 from here to here. Okay? Yeah. So R1 times from here to here is how much? 250 plus 70 plus 100 plus 125, which is 550. And that should equal to this 6.8 times this plus this, 225. Okay? So then you can solve for R1, and that gives us a certain value. Actually, I don't remember what certain. So anyway, so let's just use these numbers here. Okay? So it'll give us kilonewton for the R1 at here. Once you get the R1, then your MB, right, the bending moment, okay, at this B location is R1 times the distance, which is 250 plus 75. Okay. And that gives us this guy times this one. It's approximately 695.5 Newton meter. So this is your MB value here, right? This is your MB. Okay. Once we get the MB, then we can calculate the sigma A at this MB location. Okay. So for the sigma A calculation, you need to consider the fatigue stress concentration, because this is a fatigue loading scenario. And for fatigue loading, doesn't matter whether it's ductile or brittle material, you need to apply the fatigue stress concentration factor, so which is a Kf, times the nominal value, which is MB times half of the diameter, and then over I. Okay? Yeah. And the other thing you have to also be careful is the B location is the shorter location. There are two diameters. There's a smaller diameter 32, and there's a bigger diameter 38. So you gotta be careful that you should always use that smaller one, 32 millimeter there. Okay. Yeah. And the I calculation is pi d to the power 4 over 64. Okay. And MB is this value here. Okay. So you can calculate this portion. Okay. No problem at all. Now the Kf is the fatigue stress concentration factor. So you need to find this Kf first, right, before you can calculate this sigma A. Kf formula, because this is the normal stress, so Kf formula is 1 plus Q and Kt minus 1. Right, that's your fatigue stress concentration factor calculation. Okay. Kt, we have to find a Kt. We also have to find this Q notch sensitivity. Okay. To find the Kt, use A-15-9, right, to find Kt. Okay. The lecture notes has that figure over there, and the reason is because that A-15-9 is exactly a description, right, of these loading conditions. Okay, so this is the loading condition here, right? Yeah. So you can use the table, use appropriate dimensions given by the shaft, and then find the Kt value. Okay. So this Kt, you have to look at the table to find, and then you find that it's approximately 1.65, okay, from this table, the figure. And the Q value. So we're going to use, okay, this formula to calculate this Q value at here. So 1 over 1 plus root A over root R, and if you recall that the root A at here is called what? What do we call this root A here? It's a constant. It's called Newberg constant, right? It's Newberg constant. And there is a fairly long formula for this root A. Okay, there are two formulas. One is for Q, and the other is for the Q shear. So when you have a torque, okay, and this is bending, so you need to use a formula. This one is 635A formula they have to use, but that formula has to be modified slightly because The unit in this question, if you recall that the unit is what? It's the standard unit, okay? Standard unit here. When you have a standard unit, that root A has to be modified. Basically, whatever SUT value that you find, your SUT value to find is probably in KSI, so you divide it by 6.898. Okay, so anywhere that SUT divided by this, and then multiply by 25.4. This is basically a root millimeter unit. So that 6-35A needs to be modified to do this. All right? Yeah. So the question here given is AISI 1050 co-drawn material. Okay, so basically this portion right here. So SUT is already actually converted. So this portion right here, SUT is 690 megapound for AISI 1050. Okay, this can be from the table A-20. Okay, so if you look at A-20, you'll find this SUT value. Okay, yeah. So I'll show you the Excel. You see that I have an Excel here. How you can calculate this one here. Let's see where the root A is. So here's the root A. Okay, so here's the root A here. So SUT over 698. Let me see SUT. So 690 megapi here. Okay, yeah. So that's your root A formula. Where to go? Here. Okay, that's your root A formula. Okay, yeah. At the end, times the square root 25.9. Is that good? Yeah. Okay, so for this one here, then you can calculate it. You get your root A, which is equal to 0.313 root millimeter. Okay. So once you get this root A, then you substitute this root A here into this formula, and R is a 3 millimeter, so the fillet has 3 millimeter fillet. Then you can calculate the Q. So the Q at here is approximately to be 0.847. Okay, 0.847. Yeah. So then you can calculate your KF now. So KF is approximately 1.55. Once you have a KF, you have your sigma A, your amplitude of the complete reversed stress. Okay. So that equal to KF times M D over 2 over I, and which is equal to 335.1 megapound. Okay. So here is the stress at the B location. That's the amplitude of the stress, right? And the question, ultimately the question asked for is, how many number of cycles will the part fail? Or even the question will, basically we don't know yet, right? Is it going to be an infinite number life, or is it going to be a finite number life? So to estimate number life, you use this formula, n equal to sigma A over A and 1 over B, and A value is taken as F SUT square over SE, and B is taken as negative 1/3 log F SUT over SE. Okay, so this is the formula for us to estimate the number of cycles. So if I look at this formula, I got my sigma A already. And A and B value depends on SUT, that's okay. And also depends on the endurance limit, SE, which we haven't calculated yet. And F is called the fraction, fatigue fraction, right? The reduction fraction. So that can be found from our table there. So we'll find it at F there, okay? Yeah. So first of all, let's find F at here. So SUT, as we said, is a 690 megapound, and that's approximately 100 KSI. Okay, 100 KSI. So you can use one of the figure, I think in the handouts I gave it to you already. The handout, there's a figure 6-18. Okay. from this figure, you can find the F with 100 KSI, and that F is found to be approximately 0.844. Okay, something like that. Yeah. So now we only left with SE. We need to find the endurance limit. So for SE, and that equal to KA, KB, KC, okay, and KD, KE times SE prime. Okay, so there's a lot of factors related to SE. First, find SE prime. SE prime is the lab condition endurance limit. Now, if you have a table, you could look at the table, but typically you don't have a table. And we use basically SE, we use 0.5 SUT, okay, to find this SE prime. So SUT is 690 megapop, and then divided by 2, so you get 345 megapop. Okay, so that's your SE prime. And now dive into each one of the terms here. Okay, so sometimes you don't need to calculate each one of the terms. Really based on the description of the question here. Okay. Ka, typically you will. Ka is a surface factor. Okay, so surface factor. Surface factor is basically you look at this question here. What type of surface is it? So the question says it's a 1050 cold drawn steel. So this cold drawn, these keywords tells you the surface type, right? It's cold drawn, and you can take a look at which figure is it again? Figure table 6-2. Okay, so this table is 6-2, which is this table here. Okay, this table, see that code drawn there, right? So that's the surface condition, and the SUT is in the megapop here, so it's 4.5 times SUT to the power B, which is this value. So you get your Ka equal to 4.51, and SUT value to the power of the B value. Okay, and the calculation will give you 0.798. Good. Okay, so this is your Ka here, and then Kb. Kb is a size factor, right? Size factor here, because this is in millimeter, so everything is in millimeter for this question here. So we have to use the equation 6-20. Okay. 6-20 is for millimeter unit, and in that you look at the range of this millimeter, the actual diameter. In this here, our diameter is d equal to 32 millimeter here. Okay, so you use a smaller size d because there's a step shorter. Use a smaller 32 millimeter for calculation, and that equal to 32 over 7.62 to the power of 107, okay, 0.858. So this is the size factor Kb. And now there's Kc, which is the loading factor. Okay, and there's a different type of loading. There's axial loading, bending, torsion, right? So in this case, there's a bending, and the bending is exactly the same type of loading condition as a lab condition. So your Kc will be 1. And then Kd is a temperature factor. The question says operating at a temperature 450 Fahrenheit. 450 Fahrenheit. So we're going to use our equation 6-27, and the operating temperature is 450 Fahrenheit. There's a very long equation for that 6-27. which is this equation here. Okay, this equation. Substitute 450 into that. Okay, you can calculate your KD. So the KD calculated is to be 1.007. Pardon me? That's right. Yeah. So for that equation, so you see 450, 450, 450, 450. Yeah, everything else constant. Yeah. You can also use the table. Use the table 6-4, but you probably have to do a interpolation probably. Yeah. Then Excel, I'll give it to you. I have it programmed here, so basically you can just plug it in, you get the KD, right? Yeah. So once you get to KD now, and the last one is reliability factor. Now the question give you is 99.99%. And in this case here, we're going to use table 6-5. So you look at table 6-5. Actually, I don't have the table here. So if you look at the table 6-5, there is an exact reliability 99.99. So you can find the KE easily. That's 0.702. And that's all the factor, right? That's all the factor that's involved in it here. Then your SE equal to all of the factor multiplied together and then multiplied by SE prime. And together this is equal to approximately 167 megapop. Okay, 167 megapop. So you have SE is 167 megapop. And you have your sigma A. If you look at the calculation, sigma A equal to how much again? Sigma. Where's my sigma A? Oh, 335. Okay. So this value sigma A is much bigger than the endurance limit SE. So your immediate conclusion is the part doesn't have infinite life, right? Yeah. So which means if you need to estimate the number of life using this formula here, that n will be less than 10 to the power 6. Okay? Yeah. So when you use a calculator, use that as a sort of a threshold to verify. So you plug in this SE at here into this formula, into the formula here and here. You can calculate A, you can calculate B, and then plugging A and B here, you can calculate the n here. Okay, so all in all, you can get your A value is 2031. You can your B value is this much, and then the number of cycles is 2.13 times 10 to the power of 5. Okay. So this one is it's a complete example, basically from a simple loading condition to finding all of these marine factors, and then doing an estimation of the number of cycles. Okay. Yeah. As I mentioned in the previous lecture, when you do the calculation, just be very careful in terms of the calculation. You're using your calculator to calculate this. Okay. Sometimes I see students having trouble finding a value using a calculator for the log. Okay, so I also wanted to emphasize for now, okay? So this example here, right? This example here is for completely reversed loading. Again, this is for complete reverse loading. So here's a loading condition. If you look at the stress value that is felt by the B location, you have a complete reversed stress with a sigma A. And only this condition you use this in here to find the number of cycles. Okay? Because the next topic, so then we're going to have a slightly different type of a loading condition. Instead of completely reversed, we're going to have basically a so-called fluctuating simple load. Okay. Any questions so far on this example here? Okay, good. Okay, so let's continue in it here. So then we'll look at the next topic, which is basically fluctuating Okay, simple load. So we'll look at the fluctuating simple load, and then we're gonna end ourselves with a set of basically fatigue failure theories. Okay. Okay. So first of all, just to jog your mind, what is the fluctuating type of load, right? Now, if you remember that we covered basically when we start the fatigue loading, we mentioned about 3 different type of loadings. One is completely reversed, and the second one is called what? The repeated loading, right? So repeated to 0 and then come back, 0, come back, right? Yeah. And the third type is this fluctuating type of loading. So fluctuating type of loading is this type of loading. So you have a sinusoidal curve, okay, that has a non-zero mean value. Okay, so we call that sigma m. Okay, so here is a sigma m here that's non-zero, and of course you have your sigma max at here and a sigma mean at here. At the same time, you have your amplitude sigma a, right? Okay, this is basically fluctuating type of loading. It's general because sigma m is not 0, right? So sigma a is not 0, and a sigma m it's not 0. So this will give you the fluctuating. Okay, fluctuating, the wording fluctuating load. Okay. For this type of loading, some simple mathematics. Okay, so if you have a, let's say, this kind of loading at here, you can derive. There's the connection between the symbols that here is the sigma m is equal to sigma max plus sigma mean, and then over 2. Okay, so you can calculate sigma m based on sigma mean and sigma max. You can also calculate sigma a based on sigma max and sigma mean. Okay, so sinusoidal curve, and you can easily get that relationship. Okay, yeah. Now, what type of scenario will give us this kind of fluctuating load then, right? So I'll give you one scenario that actually results in the fluctuating type of load. Okay? So for example, let's say we have a shaft at here. Okay. So let's suppose this is a shaft, and this is a rotating shaft. Okay, so the shaft is rotating at an angular speed omega. If we have a force somewhere in the middle, okay, and then the shaft is supported by 2 bearings on both ends, then you can easily get the loading values on the 2 ends will be half of F, right, in order to maintain the balance. Okay. So if I stop right here, right? If I stop right here, if I ask you to do some sort of analysis, giving any other conditions, if you cut a cross section, right, and you look at the top or the bottom point of the cross section, what type of loading condition would you have at it for this case? The tension, but relate to the loading here. We have 3 different loading conditions, right? First is completely reversed, repeated, fluctuated. So if I stop right here for the shaft at here, is it what type of loading? Completely reversed, right? Completely reversed. So if you take a location right here, you have a complete reverse, just like the example we just gone through, right? You know, you calculate the bending moment at that location, then you can calculate the bending normal stress, and that bending normal stress is the amplitude of this complete reverse here. Okay? Yeah. Now if I add one additional force for loading, so let's say if I have a constant axial loading added to this shaft, right? So you see, there's a constant axial loading added now. With this addition of the axial loading P, then what type of loading now to this shaft? Right? You think about it. See, original without the P is this, right? It's this. And here is your sigma A. Okay? It's your sigma A. And if you cut a cross section here, if you look at this location, and for that location, this is basically the sigma A there, right? For that sigma A. And you have a basically sigma A here, right? Yeah. Now because the axial loading added, so anywhere on the cross section there is a what type of force? There's a P over A, right? That's the axial normal stress added. And this is a constant. Doesn't matter whether this is rotating or not, right? This is a constant. It's constantly added to the cross section. So basically at that location you will have a sigma m added to this normal stress. So which means this loading at here now becomes shifted up by a little bit with this much sigma m added here, right? Yeah. So this loading condition will give you this kind of fluctuating load, right? This kind of fluctuating load. Good? Yeah. That's one example where you can get a fluctuating load here, okay? Yeah. If this is not an axial tensile force, if this is actually a compressive force, then the whole curve will actually what? Going down, right? Okay? So, now this will bring us the next interesting question here is, so what will be this effect of the sigma m, right? What will be this effect of the sigma m on the performance of this part? Okay? Yeah. So, if you recall that, okay, if you recall when we learned completely reversed loading, and we use the so-called basically stress life diagram to sort of describe the performance of this part, right? Yeah. So that stress life diagram more or less look like this. Okay. So more or less look like this. Okay. Yeah. And for this one here, this is your sigma m equal to 0, and of course this is your SE here, right? So SE. And this is, let's say, approximately SUT approximately. Okay. Yeah. Is that good? Yeah. Now imagine now, right? You have your sigma m in presence now. Sigma m. And as we just said, there are two scenarios. One is sigma m is compressive, and the other is axial. Okay? Yeah. Now, what will this axial tensile or the compressive having effect on this curve at here? So let's think about the first one. What if the sigma m is a tension, right? It's basically axially stretching it. Okay? If this is a tension, how will that affect this, for example, this curve, or how will it affect this endurance limit? Would it basically will it having a higher SE or lower SE now with the tensile sigma m value? Lower SE. So why? Right? Why do we have a lower SE now? If you recall, when we learned fatigue loading, there's one for the fracture propagation, right? There's one thing that we mentioned. Under what condition will this fracture to propagate? Only when the stress is tensile stress, right? Only when you're stretching it, it'll progress, right? The fracture. So if sigma m is actually tension, so you will actually end up with a curve somewhere basically below this one now, okay? And that's when your sigma m is greater than, sorry, what is it? Yeah, greater than 0, okay? Yeah. Now, if sigma m is less than 0, which is compressive, so the compression force or stress doesn't result in any propagation of the fracture. Okay, so then that will actually result in a curve on top of this. So that'll be sigma m less than 0. Okay, less than 0. Is that good? Yeah. So basically, you can, let's see, if I draw a horizontal line like this, if I draw a horizontal line, okay? As you can see, for this horizontal line, maybe this is your sigma A at here, right? Maybe this is your sigma A, the amplitude here. So corresponding to the 3 different scenarios, you can see which one has longer life under this combination sigma A and sigma m. And apparently this one will have a longer life at here, right? Because this is the n here, the number of life, okay, of cycles. So that's the effect of this, basically, the presence of the sigma m at here, okay, sigma m. Then the next question here is, okay, so now basically we have sigma A and sigma m now. Okay, so this is a scenario for fluctuating loading. We have a pair of values, sigma A and sigma m in presence at here. So this is your fluctuating. Okay, this is the fluctuating loading here. If it's completely reversed, then all you have is, right, is this one here. So, if this is the case at here, right? If this is the case at here, and the question at here is basically, we want to derive certain fatigue failure criteria. Okay? We want to derive certain fatigue criteria for the fluctuating loading. Because for complete reverse loading, and there's actually, we already had the fatigue failure criteria, right? Which is what? You just compare the sigma A with, let's say if you design for infinite number life, you compare the sigma A with which value? SE, right? If you design for finite life, then you compare the sigma A with a certain fatigue strength at that number of cycles. Okay, so that's for complete reverse. So we wanted to do the same thing. We want to derive some fatigue failure criteria when you have, what you have is a fluctuating type of loading at here. Okay. Yeah. So the idea is still to do things through example or through experiments. Okay, through experiments. So it's like the experiments. Basically, it's like this. So let's say, for example, you fix your sigma m equal to 100 KSI, just hypothetically speaking, right? Yeah. So you have a sigma m equal to this, and then you let. So now you try sigma a equal to 50, for example, right? Yeah. And then you apply these 2 conditions together, and let the part start to rotate, okay? And until you see the failure, basically. But this doesn't necessarily will yield a failure. If you don't see any failure, basically you pass beyond 10 to the power 6. Then what do you do? If this doesn't work, so let's increase that to 60. If this doesn't work, let's increase that to 70, right? Until one of the value works. So basically you say, okay, that pair of value will give me an infinite, a critical boundary, right? Critical boundary there, okay? And this essentially, the experiments like this one will show you at here. The experiment results, which is basically look like this one here. Okay, so this is basically the type of experiment. Every one of the dots at here representing critical boundaries. It's a pair of a sigma A and a sigma M. For that sigma A, sigma M, it failed at this infinite number life 10 to the power 6. Okay. Yeah. So each dot corresponding to a 10 to the power 6, the critical boundary failure. Okay. Yeah. So you have a whole bunch of dots corresponding to a whole bunch of combinations of sigma A and a sigma M. Is that good? Right. So this is essentially the idea here. As we can see, I'll just try to sort of illustrate. You have a whole bunch of dots at here, basically. Okay. Yeah. And these dots at here, essentially they're corresponding to a certain pair of a sigma A and a sigma M value. So this horizontal axis at here is sigma M, and this is sigma A. Okay. So you have a combination of a group of sigma A, sigma M here, and then all of this corresponding to a 10 to the power 6 number of cycles. Okay, there's a failure at that. If it's less than that, then you are safe. If it's beyond this value here, then you have a basically finite number of life. That makes sense? Yeah.
Wait.
Yes. Yeah.
This one is equivalent to the one you just showed?
Yeah, this is basically equivalent to what I showed here. Those dots. Yeah. Yeah. So now with the experimental results that are here, right? And so the next step is essentially how can we come up with a failure criteria, right, to prevent, let's say, for example, certain failure at the infinite number of life. So it all boils down to how we can do a curve fitting using this whole bunch of data here. So you have a whole bunch of data here. If we do a curve fitting using this data at here, right? Using the data. So I'll move this curve down a little bit here. Okay. One way to basically to approximate this data here is do this. So you start here is your SE at here, right? It's basically, so this is your sigma A axis. So this is your SE. Okay. So you create a straight line from SE to SUT. So basically create a straight line from here to here. Okay? Yeah. So let's say if they make sense or not, right? Make sense or not. So for example, for the vertical axis here, for this axis here, what's the nature? Sigma M equal to the vertical axis here, sigma equal to what? 0, right? To 0. Okay? When sigma M equal to 0, it's basically what type of loading condition? It's the completely reversed loading condition, right? Yeah. When it's complete reversed loading condition, which value corresponding to 10 to the power 6? SE, right? It's SE, so endurance limit. Now if you look at this particular value at here, and this is your corresponding to what? Sigma A equal to 0. If sigma A equal to 0, this is actually what kind of loading condition? When sigma A equal to 0, you have only sigma M. There's no oscillating for stress. There's always a static, right? So basically, you have a static loading condition at here, right? Yeah. And with static one, when the static stress is SUT, it basically breaks, right? Breaks. Okay. So that's the two extreme here, right? Yeah. So this is the first a curve fitting that can be used, and the second one here is a little bit conservative. It connects SE and SYT at here. Okay. SE and SYT. Okay. That's the second one. Yeah. And then another type is, instead of using straight line at here, another type is to use a curve. So from here, it's a curve, okay, connecting SE and SUT. Okay, there's another one in here. And the fourth one is to use a curve, okay, connecting different color here. Let's use the purple. Okay, then it's connecting this SESYT using a curve. Okay, using a curve at here. So each one of the line at here, it's a boundary separating infinite number life from finite number life. So let's see if I use this blue color line here. So below the line, how many number life? Infinite, right? Beyond that, it would be finite number life. Okay? Yeah. Anywhere on that line is how many number life? 10 to the power 6. Yeah, which is also infinite, right? Yeah. Okay? Yeah. So if you pick a point here, it is all 10 to the power 6 number cycles theoretically. Okay? Yeah. So there are names associated with each one of the line at here. For the blue one, okay, this is called modified Goodman line. Okay. The black one here is called Gerber line. Okay. And then the green one in here is so modified Goodman. And this one here is Gerber. And this green one here, this is called Soderberg. Okay? Yeah. The purple one in here is called ASME, elliptic line. Okay? Yeah. Each one of the line has an equation associated with it, and that's where the handout that you see, I give it to you. Okay? So the handout actually lists the equations for each one of the line there. For example, right? For example, modify Goodman. Let's see. Okay. Let's see, modify Goodman line. I'm talking about just the line equation. If that line equation, modify Goodman line has this equation SA over SE plus SM over SUT equal to 1. Okay? Yeah. So modify Goodman line has this equation at here. So SASM at here, okay? So SA at here, okay, is the so-called limiting value for so SA basically is a special value of the sigma A. It's the limiting value for sigma A. And SM, it's the limiting value for sigma M. Okay, sigma M. So basically, for example, this blue color line, which is the modified Goodman line here, right? Yeah. If you pick a point at here, so you have a value, a pair of value SASM, basically. Okay. Yeah. And this value, of course, it's a special value of sigma A, sigma M. So we use sigma A, sigma M as a general state of stress, right? So this is a general state of stress. And that could fall right on the line, of course, right? But the special value, it's like this SM are like a two strength values. So they are limiting values for the sigma A and a sigma A. So this is basically, these two are sort of like a strength values, okay, for SA and SM. Okay? Yeah. So if you just interested in the line equation, okay, just line equation here, and the symbol is SASM. If we're interested in calculating is the safety factor, right? It's a safety factor. Then we replace this with the actual sigma A, sigma M, and that's basically what you see in the handout. Okay? It's just 1 over that equation, then you get your safety factor, which is what we call the fatigue safety factor. Is that good? Right? So, for actual states of stress, which is the sigma A, sigma M, right? That's the actual value, sigma A, sigma M. Then fatigue safety factor, the NF in terms of the modified Goodman line, is 1 over sigma A over SE plus sigma M over SUT. So that's the equation for the fatigue failure safety factor. And then of course you can have if you choose different lines or different criteria, then you have basically different safety factor formula. Okay, yeah. So take a look at this one here. So that's basically your formula sheet. Okay. Yeah.
Does that fatigue safety factor only apply for the modified Goodman line?
Yes, this is just for modified Goodman line. So this is basically if you choose modified Goodman criteria, right? And this is how you would calculate the fatigue safety factor. Yeah. And as a matter of fact, okay, if you look at those formulas here, if you look at all the formulas here, okay, I want you to do a quick check. If you set sigma M to be 0, set sigma M to be 0 in the 4 formulas here, what do they end up with? If you set sigma M to be 0, the NF will end up with distortion energy? No, if sigma M equal to 0, this formula becomes what? SC over sigma A. This one is same thing. This will be the same thing. There will be the same thing. So sigma M equal to 0 corresponding to the complete reversed loading, which is this formula here, right? So that basically what I'm saying is the fluctuating fatigue criteria, right? It's a general formula that includes that complete reverse loading formula. Okay. Yeah. Okay. So let me go back to this diagram here. Okay. Let me go back to this diagram. Now there is one more basically criteria. So this one more criteria is you connect this SYT. Okay. And it goes up here. There's another SYT here. So you construct yourself with a straight line here, connecting SYT and SYT on the both of the vertical and horizontal axis. Okay, so there's one more criteria. Now this red one here is called first cycle yielding. Okay, the first cycle yielding. Okay, why is it called a first cycle yielding? Because this essentially is sigma A plus sigma M equal to SYT. If you pick a point from that line, every point corresponding to a pair of sigma A, sigma M, the addition of the two is a SYT, basically. Okay? Yeah. So if sigma A plus sigma M equal to SYT, you know, from the static loading point of view, we're at what? We're basically at this yielding condition, right? So that's why this is called first cycle yielding line at here. Okay? First cycle yielding. So let me ask a question now, right? Let me ask a question. Let's say assume you're going to use modified Goodman line. Okay, so let's say you're going to use modified Goodman line here. So the first question is this. So using modified Goodman line. Okay, modified Goodman line for infinite life design. Okay, for infinite life design. If you are going to use the modified Kuhlmann line at the same for infinite life design, at the same time, also consider first cycle yielding. Okay, so at the same time, also consider this first cycle yielding. Can you draw the safety boundaries based on these two conditions? Right. So here is the criteria. So this is your modified Kuhlmann line here, right? You're designing for infinite number life. So if we're designing for infinite number life and this is your modified Kuhlmann line, so technically speaking, we should restrict ourselves to which region? To the region below this line here, right? Okay. Now on top of that, then add another condition. If we're also considering the first cycle yielding, then how would that safety region change? You know what I'm saying, right? So this is a modified Kuhlmann line. So this is your boundary here, right? This is your boundary. Okay, originally this is boundary here, but now with the first cycle yielding now, so your boundary goes from here, and then next what? Downwards here, right? Yeah. So this will be the region restricting to that two conditions. Okay. Yeah. Second question. Okay, look at this curve here. Can you tell me which criteria guarantee the design for both infinite number life and no first cycle yielding? Soderbergh, yeah, right. And this is actually the most conservative one here. Okay. Yeah. So that's sort of the understanding of how each one of the criteria works. Okay. It's fairly straightforward. Okay. Just a couple comments again. Okay, a few comments right here. Yeah. The drawing that I showed, that you know, the curve, the boundaries I showed. Okay, and also the formulas that show there. So all of these criteria. Okay. All of these criteria listed above. Okay. They are all for this sigma m greater than 0 or equal to 0. Okay, so this is basically when sigma m is in a compressive. It's in a tensile type of value. Okay, yeah, and also all of these above criteria listed above. Okay, they are all for ductile material. Okay, they are for ductile material. Okay. So let's take a look at an example here. Okay, let's take a look at an example. So this is a sort of hypothetical example. The results that are here, let's say, just hypothetically coming from some previous calculation. So I'll write down some of the results here. So let's say we have a steel bar, so which is a ductile material, of course. Suppose we have a maximum sigma max is 60 ksi, and sigma mean is -20 ksi. Okay. Yeah. And we have the material property SUT is 80 ksi, and SY is 65 ksi, SYT. And this bar, suppose maybe under certain type of loading and certain working condition. So we already let's see, suppose we already calculated the endurance limit, which is calculated to be 40 KSI. Okay. Yeah. Now we're going to use a fatigue strength fraction factor F. Okay, we'll let this guy to be just a 0.9. Okay, so fatigue strength fraction that equal to 0.9. Okay. So first step, okay, use the Goodman line here. Use the Goodman criteria to calculate the safety factor. Okay. If NF is less than 1, so second step, if this is less than 1, then estimate the number of cycles to failure. So that's this question. Okay, so let's go ahead and then do the first part here, right? We have what we're giving is sigma max, sigma min. In order to use modified Goodman line, we had to calculate sigma A and sigma m. So calculate sigma m using the formula that presented at the beginning. Okay, so here's the sigma m. And then plug in the number 60 minus 20 over 2, which is 20 KSI. Okay. And calculate sigma A. So sigma A is going to be a positive number always, so you can use the absolute sign there, but in this case it really doesn't matter. So you get 40 KSI out of here. So get your sigma A and sigma m now. Okay. Now we can apply our Goodman criteria. So Goodman criteria says NF equal to 1 over sigma A over SE plus sigma m over SUT. SE we have assumed already corrected and find them. Okay, find it. SUT is 80 and SE is 40. So that basically has 40 over 40 plus 20 over 60. Sorry, 80. Yep. And then this gives me a number exactly at 0.8. Okay, 0.8. So 0.8, what does that number mean, right? This is a number less than 1, of course. So if it's less number than 1, so basically means you will have a fatigue failure, and the number of cycles will not be more than 10 to the power 6. Okay? Yeah. So that's basically the idea here. And then, of course, the next question is, how many number of cycles, right, will it fail? Okay, if it's if this is a finite number of cycles, so here you have basically finite life. Okay, if it's a finite life, then how many number of cycles? N, right? Okay, that's the point. Okay. At the beginning of the lecture, we had an example to estimate number of life. And in that example, if you recall that, how do I calculate the n here? So n equal to sigma A over A, 1 over B, right? And A equal to F SUT and SE, and the B equal to this. This is the formula that we used for that example, right? For that example. However, if you look at this example, so what's this? When we use this for that example, what type of loading condition in that example? Exactly, right? And this example is what? It's a fluctuating, right? It's different. Basically, in that example, you only have sigma A. But in this example, you not only have a sigma A, you also have a sigma M. So bottom line is you can't just directly reuse this same formula, right, for calculating this n at here. Okay, so that's the point. So what we have to do is we don't have to modify too much. This is basically the formula here. So what we want to is, the objective is to find a so-called sigma equivalence at here. So this is basically called, we find an equivalent completely reverse stress. Okay, this guy here is called equivalent complete reversed stress, which means that what we're trying to find this one, and which does basically same damage as a pair, the sigma A, and the sigma M pair. Okay, does that make sense? Yeah. So you have currently it's a pair of sigma A, sigma M, right? And we want to use this equation, but we can't just plug sigma A into this equation. So we want to find an equivalent complete reversed stress, sigma ReV, which does the same damage as this pair here. So if you can find this, we can just plug in the sigma ReV into this formula here. Okay? Yeah. So how do we find this equivalent here, right? So let's go back to the modified Goodman line here. So modified Goodman line here is what? This is your SE at here, and this is your SUT, right? Okay. So here is your Goodman line. Okay, here's Goodman line. So what's the nature of a Goodman line here? So if let's say, you remember what I said when we talk about this criteria here. If I pick a point here, here, right? Pick up any point on this modified Goodman line. What's the commonality? Every one of the points will have a life the same as which number? 10 to the 6, right? Very good. So currently, right? This is the current state of stress. Currently, you find a coordinate because we know it's not going to be infinite number of life. So the current state of stress, let's say probably is here. Here is your sigma A, sigma M. It's outside the boundary, right? Outside the boundary there. You have a finite life. Okay? Yeah. So I'm going to use a similar logic here. I will create a line by passing through this current state of stress and connecting this SUT. Okay, connecting SUT. See, this is basically the similar way of constructing the modified Goodman line, right? So you create a line here, like you create a line like this. So this side here is called SF. So this one here. So if I use a similar analogy, if all of the red dots here has 10 to the power 6, then if I plug in all these black dots at here, what's the commonality? All the black one in here should also have the same what? The same number of cycles, right? To feed here. Okay? So then the extreme here is this one. And this is basically what condition? When sigma m equal to 0, which is the condition corresponding to the completely reversed loading, right? Yeah. So this value here is the sigma ReV we're going to try to find. Okay? Yeah. So this complete reversed loading here will cause the same damage as this pair sigma A, sigma M, basically. Okay? Yeah. So how do we find this thing here? It's actually pretty easy because you connect this point with this point to construct a line equation at here, right? And then you can find basically your sigma ReV. Okay. Yeah. So, for example, right, this line right here, so modified Goodman line is what? It's SA over SE plus SM over SUT equal to 1, right? Yeah. Then for the green one in here, if I use the same logic, so it's going to be sigma A over, so if you compare here, sigma A over which value? Over this point value, which is sigma REV, right? And then plus sigma M over this SUT and equal to 1. Okay? So I solve for sigma REV, so solve it, you get your solution for sigma REV, sigma A over 1 minus sigma M over SUT. Okay? See, that's the formula, basically, for sigma REV here. Okay? Okay, so I have a sigma A, sigma M given already in this question, so you can calculate this one. This turned out to be 53.3 KSI. That's your sigma REV. Okay. Once we get our sigma REV now, then we can estimate the number of cycles now. This is basically first calculate A value. Calculate A value, that's F SUT over SE square here. Plug in number 129.6. B value is negative 1/3 log SUT F over SE negative 0.0851. Okay. Then your number of cycles N is sigma REV over A to the power of 1 over B. Okay, plugging all the numbers, there's 3.4 times 10 to the power of 4 cycles. Okay, that's right. Yeah. Yeah, that's right. Okay. Good. So this is basically a different perspectives, estimating the number of cycles when what you have is a fluctuating type of loading. Okay? Yeah. Very good.
Oh.
Yes.
Does that equation for the sigma REV only work for
Goodman?
as well?
That's right.
Sorry.
Yeah. You can use a similar approach if, let's say, if you're using Gerber, right? I'll see myself the derivation. If you're using Gerber, your sigma REV will actually be this formula. Okay, will be this formula. Okay. So let me finish one more small topic and then we can call it a day here. Okay, any questions so far? Okay. It's all good? All right. Okay, so the examples that are given and also the feeder criteria is derived. What they all have actually focused on is the normal stress, right? You know, basically completely reverse the normal stress. Okay, and then you have a pair of a sigma A and a basically sigma. So what if basically it's actually torsion, right? What if it's a torsion? And actually it's a fluctuating, let's say fluctuating, basically instead of a sigma A, sigma M, it's tau A, tau M, right? So fluctuating torsion here. That's another example, simple. So it could be fluctuating torsion here. So we don't need to rederive everything. We can use the existing formula right here to do some replacement to derive the feeder criteria for torsion here. So I'm going to use the Goodman line here, for example, here. Okay? Yeah. I'll use Goodman line criteria, okay, as an example. So what do you do here? It's very simple. Okay, so replace sigma A and sigma M with tau A and tau M. Okay, so wherever the sigma A, sigma M in the Goodman line criteria, just replace that with tau A, tau M. And second of all, okay, use the Kc equal to 0.59 for calculating SE. So SE is in the Goodman line, and when you calculate SE, make sure the loading condition Kc value, the marine factor, is 0.59, because 0.59 corresponding to the torsional loading. Okay, and then replace SUT with SSU. Basically, replace the ultimate tensile strength with ultimate shear strength, and there is a approximating formula between these two. So 0.67 SUT. Okay. Yeah. Now, if you're using some other criteria, maybe you require the SYT. So then you're going to replace the SYT with SSY. So it's a shear yield, and which is 0.577 SYT. And 0.577 SYT, if you recall, that actually is a result from the distortion energy theory. Okay. So now you can obtain the modified Goodman line criteria for torsional type of fluctuating loading. Okay. Yeah. So that's basically what you do for this one here. Okay. And of course, for first cycle yielding, originally it's sigma A plus sigma M, right? So SYT over that equal to safety factor. Now it will become, the NF will become, SYT is replaced with 0.577 SYT, replace that with SSY, and then tau A plus tau M. Okay. For torsion. Okay. All right, so I'll stop here. So, and that's basically, there's one little bit left on fatigue theory, and then we're ready to go into different machine elements. Okay. So I'll send another email regarding specifically what the midterm will cover. If I jog my mind here, probably just cover until what today's lecture says. Okay? Yeah. So, any questions? Good. Yeah. We're already calling what these I see.